to the SNAPP seminar series. Today's speaker is Professor Thodoris Lykouris. He's an assistant professor of operations management at MIT in the Sloan School of Management. Before joining MIT, Thodoris received his PhD in computer science from Cornell University, and then he worked as a postdoctoral researcher at Microsoft Research, New York. His research focuses on data-driven sequential decision-making and spans several areas such as machine learning, optimization, and economics. Thodoris has received many awards for his work, including the Google PhD Fellowship, and he was also finalist for the Danzig Dissertation Award, Nicholson Student Paper Competition, as well as the Applied Probability Society Student Paper Competition. So with that, let me welcome Thodoris and can start when you're ready. Quick comment on the format of the talk. So Thodoris welcomes questions during the talk. So if you have any questions, feel free to type them in the chat or raise your hand and ask questions, or we'll also have an opportunity for you to ask questions at the end of the talk. Also, his talk slides are available on the SNAPP seminar website. So if you want to download them and follow along, you can do that as well. So with that, let me hand it over to Thodoris.
Thanks, Gauri, for the warm introduction, and thanks to the organizers for inviting me. So today I will talk about learning to differ in content moderation, the human-AI interplay. This is joint work with Wentao Weng, who is a PhD student at MIT. Wentao is in the audience, so if you have tough questions, feel free to ask on the chat or clarification questions as well. But also, questions during the talk are more than welcome as well. So if we think about the beginning of the century in the 2000s, and if you think about how forums used to work, or they work even now, you used to have a moderator that would read all the posts that were posted and would try to understand which posts should be removed from the platform and which posts should stay on the platform. So this moderator tend to be very reliable because they knew exactly what type of posts should stay on the platform. But also this process tends to be pretty slow because the moderator would need to actually see every single post and decide which of them to remove. Now, fast forward to today, if you think about social media, you cannot hope to have a human review actually all of those posts. So you need a process that is significantly more responsive. Fortunately, we're in the era of generative AI, and you have a lot of opportunities actually to have good AI systems that can have pretty good predictive accuracy about whether a post is going to be harmful for the platform or not. That said, AI tends to be also prone to errors. So, whenever you try to automate these traditional human-centric systems, these errors actually can have significant risks. In content moderation, maybe when you have those errors, you will end up in a situation where you are going to leave hate speech, for example, on the platform, or maybe you're going to censor perfectly legitimate speech. And although this talk will be about content moderation, the ideas that I describe apply broadly to other human AI systems. For example, if you think about an insurance company like Pingan, whose business model is to just automatically reimburse all of the claims within 3 minutes, then there are risks of fraud and potential wrongful rejection. Similarly, if you think about call centers, it's great to have an AI chatbot deal with the customer support service in an automated fashion, but we also, a few weeks ago, what happened with Air Canada, that essentially they needed to pay the refunds that the AI chatbot promised. And similarly, people have tried to use large language models in order to write legal briefs. And of course, large language models may hallucinate. So these lawyers ended up getting fired and fined. So I want to highlight essentially that there are many risks when you try to automate traditional human-centric systems. So the typical approach that one can try to do is what I call human AI pipeline in order to mitigate those risks. So I will describe that within the focus of content moderation. As I said, many of the ideas would apply to other settings as well, but I will describe that for content moderation. So when a post arrives, immediately you need to make a classification decision. You need to decide do I keep the post on the platform, or do I remove the post from the platform? Now, this decision is not irrevocable. We could, in principle, later decide to overturn this decision. Maybe you keep the post on the platform immediately, but after some time you decide that this is harmful and therefore you want to remove it. But you need to make some decision initially. And then you also make a decision of whether you're going to send the post to human reviewers. This is an admission decision. Do I admit the post to a queue that eventually is going to be reviewed by humans? And finally, the last decision you need to make is that from the posts that are already in the queue, you need to decide which one to schedule, which post is going to be scheduled to the human reviewer when such a reviewer becomes available. So the main question in this talk is how can we make these three decisions? How can we make the classification decision, the admission decision, and the scheduling decision in a way that achieves the best of both worlds in some sense, combines the responsiveness of AI with the reliability from humans? So this is the high-level question that we are going to be interested in. Now, let me give you some data from Facebook just to motivate the setting further. Anybody has any idea about how many posts are posted to Facebook every month? So the answer is something like 60 billion posts every month. So this is data from last year, but I don't expect that they have changed significantly. How many human reviewers does Facebook employ? The answer for that is 15,000. So if you do the math, you're going to soon realize that if you wanted that every post would go to a human reviewer, you would need each reviewer to review something like 4 million posts per month. And if you do the numbers on an hourly level, you can soon realize that this is completely unrealistic. You cannot hope that every post is going to be reviewed by humans. So let me give some of the quotes from Facebook community standards just to further motivate the setting. So one quote says, whether potentially violating content is reported by people or detected by Meta, Meta's technology, automation helps us quickly route the content to reviewers. So AI will help us decide which posts are going to go to reviewers. We then use technology to prioritize content so our review teams can focus on the most important tasks. So really, because reviewers are more reliable, we would like them to focus on the most important tasks. A second quote says, our technology does well in detecting repeated violations and identifying obviously graphic or extreme content. So AI is pretty good for many tasks, but when there is a high degree of ambiguity, complexity, or nuance in whether our policies apply to a piece of content, reviewers tend to make better decisions on technology. So human reviewers are actually more accurate. So AI can be much more prone to errors compared to human reviewers. And finally, when reviewers make a decision about a piece of content, they are simultaneously training and refining our technology to help it identify other pieces of similar content over time. So this human technology feedback loop is vital to keeping our systems current. So the reviewers do not only have an enforcement role in deciding which posts should be removed, but they are also providing labels that allow the AI to run better in the future. So let me give the pipeline of the content moderation. When a post arrives, there is an AI review. When this review happens, we need to make an immediate classification decision. We need to decide whether to accept the post. This means that the post is going to remain on the platform, or whether we want to reject the post. This means that the post should be removed from the platform. Then we also need to make an admission decision. Essentially, we need to decide whether to defer the post to human reviewers. And if we defer the post to human reviewers, it will enter a queue. And finally, we need to make a scheduling decision. When a human reviewer becomes available, we need to decide which of the posts that are currently on the queue should go to the human reviewer. And as I said, the role of the human reviewer is dual. On the one side, there is the enforcement role, because potentially the human reviewer may realize that the initial classification decision that we made through AI is actually inaccurate and we should overturn it. But it also has a labeling role, because it provides labeled data that can allow the AI system to run better in the future. Now, I want to mention that in learning theory, this feedback structure, where you only receive labels for posts that you selected to receive labels, is called selective sampling, and it's a useful term to keep in mind, essentially. So now that we have the content moderation pipeline, the main question is, again, how can we make this classification, this admission, and the scheduling decisions in a way that combines the responsiveness of AI and the reliability of humans.
Thodoris, you said
Yes,
we
I'm
could jump in and ask you questions. So clarification,
very
how
happy.
long can things be in the queue? Am I talking about an order of a second, a day, an hour?
Good. So they can be on the queue as long as you want, but typically after some time, users will stop engaging with the content. So reviewing it after this point will be a little bit less useful because all the harm has been done. So
Yeah, I'm thinking that some of the content will be not useful anymore. It'll kind of expire if I don't make a decision in, I don't know, an hour or.
Right. So in the model, I will formalize the model afterwards. In the model, essentially, we are assuming that the post will have a lifetime. And as for whatever time you have made the wrong decision, you are going to incur some cost. So if you delay a lot, you are going to incur a lot of cost. If you make an immediate decision, you're going to incur less cost, essentially. So to answer your question exactly, the post could stay on the queue for as long as possible. And sometimes it may be useful to actually review an expired post because of the labeling component. Maybe for the enforcement component, it will be less relevant because you already have accumulated all the error or the cost essentially from this particular post. But maybe you want to review a post from even a couple of days ago because this will help you do labeling for future posts. Does that make sense?
Yeah, thanks.
Yeah. And I will formalize the model. I think it will be clear when I describe the formal model. Yeah, good. Other questions on the high level? So this is kind of a high level picture. I will go to the formal model in a couple of slides. Before going to the formal model, I'm going to describe the two heuristics that one would try to operate in these settings. And I'm going to identify challenges in doing so. And this will help us understand what is challenging about the model. So what's the first heuristic? The first heuristic is, let's not use any AI. Let's go back to the 2000s and have an automation-free heuristic system. So every post goes to the human reviewers, and the human reviewers are going to make a determination for the post. Now, if we remember from what we said about the Facebook data, this is completely unrealistic. You cannot hope that the posts you are going to have a human reviewer review all those posts. So what we will have is that eventually the queue is going to overflow, and therefore you will have extreme delays in this human-only system. So really the challenge, and this comes back to Amy's question, is that if you send too many posts on the queues, it will take a significantly longer time until the posts are eventually reviewed. And with these numbers, actually, you will not hope to review all of the posts anyway. So this is the challenge of not using AI at all. Now, the typical way that humans and AI interface in these systems is via the following approach. We set two thresholds, a low and a high threshold. And the AI will output a score that says, for example, what's the probability that the post is harmful, or what is the expected harmfulness of the particular post. Now, note that this score could also say that with high probability the post is a good post. So if the score is lower than the low threshold, then what we're going to do is we're going to accept the post and we're going to keep it on the platform. If the probability of being a harmful post is very close to zero, for example, you don't want to reject it, you have value of keeping the post on the platform. Now, if the score is very high, so if it's very likely that it is harmful, if it's above the high threshold, then you're going to remove the post. And in both of these cases, you don't send it to humans. Now, if the score lies within the band between the low and the high threshold, then you're going to defer it to human reviewers. You will make some initial classification decision, but you want to also potentially check again with humans to potentially overturn this decision and have a better idea. So this is the typical pipeline that most systems are using, and this is described actually from papers from Facebook, from the Central Applied Sciences Facebook, but also it's the typical approach. This idea of two thresholds is the typical approach the first approach that one would use in order to try to combine humans and AI. You want to accept if something seems very unlikely to be harmful. You're going to reject if something seems very likely to be harmful. And if it's in the band in between, you're going to send it to the human reviewers because the borderline post, so maybe you're going to to get a better idea. Now, what are the challenges in this setting? First of all, many types of posts have a lot of idiosyncratic uncertainty. So, for example, if you think of the word crazy, the word crazy could mean, it could be something perfectly legitimate if you talk about a crazy accident, but at the same time, it could be very harmful if you use it to describe a person. So a scalar score that just says what is the expected cost essentially of a post cannot really capture this idiosyncratic uncertainty. So that's a reason essentially why we may want to not have this static, these two thresholds essentially approach, and we want to try to capture the idiosyncratic variance of posts as well. The second is that arrival patterns and reviewing capacity can have very high fluctuations. And this is data again from the first paper from Facebook, which shows that the reviewing capacity is actually very, very volatile. So if you have actually two static thresholds that are determined outside of the operating system without taking into account how the human reviewers are going to operate, then you may end up in a situation where you are either underutilizing your human capacity or you may have overly congestion in the human queue. And again, from the same paper, there is another figure that also shows that when you operate at an additional load, actually the queue length of the human review queue becomes really large. And the final problem that exists with this typical human AI heuristic is that when you have these two thresholds, you're essentially only getting data from the posts that lie in the band between the two thresholds. If your score is below the low threshold or if it's above the high threshold, you will never really get any data from those. So it's very difficult to keep your systems current with respect to data that arrive in these settings. So this is a form of representation bias, and that makes learning a little bit challenging in these settings. So this gives an understanding of what are the challenges that arise when we try to use these two heuristics. So what I want to do now is I want to describe a model that will capture the setting, and then I will pause to answer any questions on the model, and before proceeding to describing how we address that. Okay, are there any questions on the heuristics before going to the model? Okay. Okay, what's our model? We assume that we have a finite number of types that is I denote by capital K. And each type has a known lifetime, and this comes back to Amy's question. So the lifetime is the number of periods that users are going to engage with the content, right? So essentially, each post will have a different lifetime, essentially, of how many periods users will engage with the content. We're also going to assume that each type of post comes with a human review rate, a rate in which humans are processing it. And I denote that by mu k. The reason why this could be different is maybe a post is a video, so it takes longer to actually see the video in order to decide whether it's good or bad, or a post may be a text, it's much easier, it's an audio, like there are different formats. So different types of posts will take different time to be reviewed by humans. We're also going to assume that every type of post has a per period cost distribution that I denote by capital Fk. And I'm going to assume that this is unknown. We do not know what is the cost distribution that is associated with every type. The only assumption that we make on this distribution is that it's sub-Gaussian. So we don't make any real assumption about how this distribution looks like. We only assume that it is sub-Gaussian, essentially. Okay? Now, again, when a post arrives, it comes with an observable type. So the way to think of it is that you will run a classification initially, and it will say, okay, the type of the post is this particular type. And I will denote the type of the post JT as KT. Now, the probability that the post will have a particular type comes from an arrival probability that I denote by lambda KT of T. And note that this can change with time, because we said that we want to allow for fluctuations in the arrival patterns. So the probability that a post will have any particular type is potentially time varying. It can be changing with the time. And then the cost of the particular post is going to be drawn from the cost distribution of its type. So Cj of t is the cost, the per period cost of a post. This is going to be drawn from the cost distribution of the type. Again, this information is something that we do not have access to. And the only way to actually get this information is by sending it to human reviewers, essentially. Okay? Any questions until here about what are these are the two parameters that I want to define, essentially. Other than that, I will describe the pipeline.
So is the cost, for example, risk of being harmful, like not taking harmful posts down during the period, or what
Yes.
is the cost?
So good. So the cost distribution, you can think of it, for example, it can be 1 if the post is harmful, or -1 if the cost is not harmful. So this goes to my next point. A bad post would typically have a positive cost, right? So essentially, if your cost is positive, then this means that the post is bad. Now, the more positive it is, the more harmful it is. Like if it's low, closer to 0, maybe it's harmful, but it's not that harmful. If it's very high, then it will be very harmful. But also, if a post is good, then it has negative cost. Because essentially, you will actually have value if you keep it on the platform. You would like to keep it on the platform. Again, the more negative it is, the more reward you're getting, essentially, from keeping that on the platform. So this cost structure allows us to capture both good posts and bad posts, and also the intensity of how good and bad the post is. So essentially, what we're saying is that every type has a cost distribution that says essentially what is the distribution of the costs of posts of the associated type. When a post comes, then its realized cost is going to be drawn from the distribution of its corresponding type. Okay?
Thodoris, could you maybe explain how we should think about the difference between a type and the per period cost
Good.
incurred
Okay.
by a given post of a
Great.
given type?
Great. So one way to think about types would be, for example, you run, I don't know, your favorite transformer, and it returns an embedding of a word embedding. So you get a post, and it will take a word embedding. This will be one type, for example. So now for every type, for the time being, I will assume that the types are finite. Later, I will also extend to a contextual case. But for every type, for every word embeddings, essentially, you have a different cost distribution. Like a word embedding would say, does this word appear? Does this word appear? For example, does this word appear? Right? And based on this different type, there will be a different cost distribution from and the realized post essentially has a cost that is drawn from this distribution. Now, at this time, at time t, we also have a reviewing capacity that I denote by capital NT. And again, I want to allow for fluctuations in reviewing capacity. So I allow the number of reviewers that you have at this particular round to be changing with t, to be potentially time varying. Okay? Okay. Other questions on these are all the parameters I have, essentially. So if there is any question about any parameter here, if there's any question, that's a good point to. Again, we have the types of posts. Think about word embeddings. When a post comes, we are going to run a transformer, and we're going to create a word embedding. For every word embedding, there is a cost distribution, a distribution of costs of posts that have this word embedding. And when a post comes, we see the word embedding because we just ran through the transformer, so it's observable, the type. And we get, and the cost is something that is drawn from the cost distribution, and this is unobservable to us. Okay? And we have both the arrival probabilities can be time varying, and the reviewing capacity can also be time varying. Okay. Now let's go to the content moderation pipeline to just formally define it now. When a post arrives, we need to make an immediate classification decision. So we need to decide whether to accept the post. This means that the post will remain on the platform, or we're going to reject the post. This means that the post is going to be removed from the platform. And we also need to make an admission decision. This means that we are going to decide whether to defer the post to human reviewer. If we defer it, it enters a queue. And once it enters the queue, we need to make a scheduling decision. essentially that says whenever a human reviewer becomes available, which post from the ones that we have on the queue we're going to send to the human reviewer. Now, we're going to assume that a human reviewer will finish the review with a rate that depends both on the review rate of the associated type. Again, if it's a video, it will take longer. If it's a text, it will take less time. And it also depends on the reviewing capacity. How many reviewers do we have? So the rate essentially is the product between the review rate of a single human times the number of humans that are available. And also we're going to assume that we will be able, the human is going to be able to observe accurately the cost CJ of t. We're going to be able to see exactly whether the cost is, for example, 1 or -1 in this case. And subsequently, we said that the humans have two roles. The human reviewer has two roles. There's an enforcement role. Potentially, they're going to finalize a classification decision. So given that they know the cost CJ of t, if this cost is positive, then we're going to reject the post. If the cost is negative, we're going to accept the post. Now, it could be the case that the AI classification decision was the same, in which case we don't do anything. But it could be the case, for example, that the AI has decided to accept the post, but then we realize that this cost is positive, and therefore we're going to overturn the decision that the AI has made. And there is also a labeling role, because we have one more label data point, the type and the cost, and this can be used by the AI to make better decisions in the future. And as I said again, this feedback structure is called selective sampling. This idea that I'm only going to get labels for posts that I selected. Any questions on the model? I have one more slide about the objective, and then I will go to the techniques. But if there are questions on the model, I think that's a good time to just make sure that the model is completely clear. If anything is not clear, it's a good time to make sure that everything is clear.
I have a quick question. Do you update the cost distribution as you get labels from posts?
So the cost distribution is ground truth. I don't know that, but I will keep an estimate, like I will try to estimate the cost distribution. So essentially what I'm doing is that as I get more and more data, my estimate about the cost distribution becomes better and better, essentially, right? So I update my estimate about the cost distribution. The cost distribution, I assume that is fixed, and it's something that's ground truth unknown, and I need to learn it or learn it well enough in order to make good decisions, essentially.
Thank you.
Other questions? Okay, let's go to the objective. So again, the important parameters that we discussed, we have types. Again, think about word embeddings. Every type will come with a known lifetime, LK, and the human review rate, μk. And there is an unknown per period cost distribution, FK. And at every time that a post arrives, it will have a type that will be drawn from a time-varying arrival probability, and it will also have a unobservable cost CJ of t that is going to be drawn from this cost distribution. Now, the cost of a post, and this again relates to the question that Amy had before, it has two terms. It's a product of two terms. First of all, it's the per period cost. How bad is it that how bad is that this post exists on the platform every time that it exists on the platform? Now, this can be large for two reasons. Maybe it's a really bad post, or maybe it will attract many eyeballs in this particular round. So many people are going to see that. Maybe even if the cost of every individual eyeball is not too large, the overall cost that we have in the period is going to be pretty large. But it also depends on the number of periods that the post is active. And by active, I mean that the post exists on the platform. And this depends actually on our three decisions. So if our classification decision was to reject the post, so remove it from our platform, and our admission decision was to not defer it to human reviewers, then the number of active periods is going to be 0. The post will never see the light of day. Nobody's going to ever see the post. We rejected it, and we did not send it to human reviewers, so we're not going to be able to overturn that decision. Now, note that we may still have error, because it could be that the post is good, and therefore we made an erroneous decision of rejecting it. Now, if we decide to accept the post, and we do not send it to human reviewers, then the number of active periods is going to be equal to the lifetime. It will stay for all its lifetime, and people are going to engage with the post throughout the whole lifetime. If we decide to accept the post, and we also decide in the admission to send it to human reviewers, then the number of active periods is going to depend on the scheduling that we do. If we if the post ended up being bad, for example, then essentially the number of active periods will be the delay until the post is eventually reviewed by human reviewers. So I want to stress that the number of periods that the post is going to be active really depends on the decisions that we are making, both the classification, the admission, and the scheduling decisions. Now, the total loss of the algorithm is going to be the time average cost across all the posts that we see, minus omniscient optimum. The omniscient optimum, we would assume essentially that it has access to the exact information of whether a post is good or bad. So if the post is good, an omniscient optimum would keep it on the platform, and therefore we are going to have a cost Cj of t. This is a negative number, so this would be this is what we would be accruing. If the post is bad, the omniscient optimum would remove the post, and therefore it will suffer a cost of 0, because the post will never see the light of day. Now, I want to stress that even if we had the information about all the cost distributions, the only way to actually know the per period cost Cj of t is by sending it to human reviewers. So this omniscient optimum is actually not something that we can realize, because this ignores reviewing capacity. This assumes that we are able to send to all the reviewers and have information about the cost. But if we operate at a limited reviewing capacity, we will not be able to get into this information for all of those posts. So instead, we need to evaluate how well we're doing. We need to compare the loss of our algorithm to a loss of a benchmark that takes into consideration the reviewing capacity, essentially. So this benchmark, the loss of this benchmark I denoted by loss star of W. W is a window. The simplest way to think of it is when W is equal to 1. When W is equal to 1, what essentially I'm saying is that we need to immediately review a post that arrives. So the number of posts that we can send to reviewers should be equal to the review rate of reviewers for any period. So when multiple posts are arriving, think of it as a fluid, essentially. Like there is a probability that posts are arriving. The total probability that we're sending to reviewers should be equal to the review capacity that we have for any period. This is a good benchmark when we think about stationary setting. To allow for non-stationarity, we extend that to be able to review posts at nearby periods. And this is inspired by the notion of capacity region that was introduced recently by Young, Strickland, and King, and also Nguyen and Modiano. And this essentially allows us to capture non-stationarity. Maybe we are going to be able to use nearby reviewing capacity to review arriving posts in nearby periods. I don't want to formalize it to formally state that. The paper we discussed that in detail, but the high-level idea is that we want a benchmark that respects the reviewing capacity. We cannot assume essentially that we have access to the exact cost of everything, because this does not take into consideration the reviewing capacity. Any questions on the objective? Okay, our main result is the following. We are going to prove a regret guarantee that says that it scales with the window size of the benchmark times square root of the number of types and the maximum lifetime, plus a term that vanishes as the time horizon goes to infinity at a rate of square root of t. I want to stress that this square root of maximum lifetime dependence is actually unavoidable. We have a lower bound that shows that even for known system parameters, this dependence, you need to pay square root of maximum lifetime. And also, the simpler heuristics that I said before, like it can be a human-only system or an AI-only system or these static thresholds with the two thresholds, all of them are going to give linear dependence on the maximum lifetime. So actually, achieving the square root of dependence on maximum lifetime can be non-trivial. We also offer a contextual extension that removes the dependence on the number of types. If you think about word embeddings, maybe the number of types will be too large. So you would like to scale with the embedding dimension in this case. And this is actually the first result for online learning contextual queuing systems. So I think it can be of interest beyond the particular application. I will briefly discuss that towards the end. I think that the techniques that we're using can be widely extendable beyond the particular setting to think about contextual queuing system and how you do online learning in these settings. So let me have a roadmap of what the rest of the talk is going to look like. We're going to start with known cost distributions, and we're going to try to understand the skeleton when we know exactly what are the cost distributions. Then we're going to already show the main trade-off of how to balance essentially this idiosyncratic uncertainty and the delay. Then we're going to introduce learning. How can we learn these cost distributions? And we're going to discuss and explore exploit trade-off in this case. Interestingly, we're going to see that the traditional ways to do learning, like UCB, for example, will fail in this case, and that you need to do something more interesting. And finally, I will briefly discuss about contextual queuing systems and what are the additional challenges to have a very large type space and how one can make progress in order to deal with contextual queuing systems. And again, I think that this can be helpful when you do online learning for contextual queuing systems, even beyond the particular application. Okay, first, known cost distributions. Let's assume that we know the cost distributions. What are the main challenges? We said that when we had this automation-free heuristic that only had humans, you would have extreme delays. Remember, we had this overflow of the queue, essentially. So you would have very extreme delays. On the other hand, this two-threshold heuristic with a low and high threshold, that you were removing everything that is on the above the high threshold, you were accepting everything that was below the low threshold, and we were sending to reviewers everything in the band in between. This disregards the idiosyncratic uncertainty of posts. Remember the word crazy, for example. And also it cannot capture non-stationarity, and it can lead to overutilization or underutilization. Remember the figures from the Facebook paper that show that these fluctuations actually arise in practice significantly. So our admission rule will try to balance these two forces, essentially. We need to first understand what is the cost of not deferring a post. If we are not going to send a post to human reviewers, what are we missing? And the cost is really the misclassification. We need to make a classification decision, and this is going to be a final classification decision. We don't have any way to overturn it. So even if we know the cost distribution, we may make mistakes. So if the cost distribution was a point mass, then we would make no mistakes because we would know exactly that the cost would be exactly this number. But if the cost distribution, for example, has some positive mass and some negative mass, we're going to either make mistake when the cost is positive, or we're going to make mistake when the cost is negative. So we're going to try to characterize what is the error on both of them. So the error, if we make an accept decision, whenever the cost is negative, we actually made the correct decision. Because whenever the cost is negative, we kept the post, and therefore we don't pay anything. Whenever the cost is positive, we actually are suffering from the post is going to remain on the platform, and therefore we're paying the cost as error. If we make a reject decision, if we remove the post from the platform, we are going to make the correct decision whenever the cost is positive, because if the post is bad, then we are removing it from the platform. But we're actually making the wrong decision when the post is good, and we are paying minus its cost, essentially. Because we are removing it, so we will have cost 0, but the optimal thing to do, the omniscient optimum, would have kept it, and therefore would have a cost Cj. Cj is a negative number, so the error will be minus Cj. So when we know the cost distribution, we can take the expectation of this cost distribution and identify exactly what is the expected per period error for an accept decision and the expected per period error for a reject decision. And then the cost for not deferring will be the number of periods in which the post is going to be active. Again, if we are not deferring it, then the post is going to be active for all its lifetime. We're not going to remove it afterward, times the minimum of the two. Because we can evaluate what is the per period cost of an accept, the per period cost of a reject, and we will take the best of the two decisions, essentially. So the cost of not deferring is the lifetime times the minimum of the error on accept and the error on reject, because we need to fix a decision, essentially, and stick to that. What is the cost of deferring? The cost of deferring mostly relates to the additional congestion that it adds on other posts. When you have a post that is added to the queue, you will cause delay on other posts because you will need to serve the post. Now, as a proxy for this, we're going to use the number of posts, the queue length, the number of posts of the same type. And this is inspired by the idea of drift plus penalty that was introduced by Stoliar and also studied by Huang and Neely. This idea that essentially you can connect delay with the queue length, essentially, in this particular case. So our admission decision is going to say, we're going to see what is the cost of not deferring, what is the cost of deferring. We're going to defer if and only if the cost of not doing so is higher than the cost of deferring. So essentially, this balances the idiosyncratic loss from not deferring and the delay loss from deferring. That's why we call it BASIT, balancing idiosyncrasy and delay. Now, I'm going to stress that this is actually a congestion-aware rule. Unlike the two static thresholds that we discussed before, here, if you have, for example, very high fluctuations and in the reviewing capacity, and you end up having lower reviewing capacity at a particular point, the queue length is going to increase, and therefore you will have a higher threshold in order to defer something. Because the cost of not deferring is not changing with the reviewing capacity, but you are comparing it with the queue length. If the number of posts that you have on your queue increases, eventually you're going to have a very high threshold in order to send to human reviewers. So this is a congestion-aware rule, essentially, admission rule. Now, with respect to the other decisions, the classification decision is very simple. Like we know what is the error on accept and what's the error on reject. We're going to just accept if the error of accept is smaller than the error of reject, and we're not going to accept otherwise. And the scheduling decision, we're going to just use max weight, which essentially says that we're going to prioritize the longest queues, the types from longest queues, but also we're going to take into account the how fast a type is. What is the human review rate? So this is the first idea. This is how do we deal with known cost distributions? The high level is that we need to use a congestion-aware rule that does not have two static thresholds, but the thresholds adapt based on fluctuations on arrival patterns and reviewers. And in order to achieve this nice balance, we need to compare the cost of not deferring with the cost of deferring. We're only going to defer when it is better to defer than not doing so.
Thodoris,
Yes.
quick question. Maybe I missed this in the model, but are you effectively treating the different types as entirely disjoint with respect to reviewing capacity? Or is there joint capacity for all? And yeah, which one is it?
It's joint capacity for all. It is joint capacity for all. You have it's a joint capacity for all. Really, what you're doing with that is that I want to connect. I cannot really argue that much about the idiosyncratic loss, so I want to connect to the queue length somehow. And really, by having these different queue lengths for the different types, you know which posts you should prioritize with respect to their cost, essentially. So there's a joint reviewing capacity, and that's the scheduling, right? When a reviewer becomes available, we need to decide which type we're going to send. We're going to send based on max weight. We're going to say, what is the queue length of this particular type? times the review rate, we're going to prioritize the ones that has the maximum weight, where the weight is the review capacity, the review rate times the queue length. So the scheduling essentially says we have this joint reviewing capacity. When do we prioritize a particular type over another?
So I guess then my question would be, when you look at the cost of deferring,
Mhm.
does that implicitly capture the congestion on other post types?
Yes.
Or does it only capture, because explicitly it only has the other posts of the same type?
It's only here as a proxy, we use the cost of the post of the same type, and this is inspired by this idea of drift plus penalty that I described. We're only going to lose a factor of k from that, the square root of k essentially for that. So that's why, if you remember the result, we have square root of k times maximum lifetime. The k there essentially is because we are going to keep different queues. And when I talk about the contextual extension, this is actually one of the challenges, right? Because when you keep a separate queue for every type, if the number of types becomes too large, you are essentially over-admitting. You are admitting for every type post, essentially, right? So when we think about the contextual extension, that's something that we would want to deal with, essentially. Make sense?
Yeah, thanks.
Other questions? Yeah. Let's go to learning. So what do we do? We said we're going to evaluate the error of an accept. If we make an accept decision, what's the error? The error of reject. And we're going to defer if and only if the not doing so is better than, is more costly than doing so. Now, the challenge when you have unknown cost distributions is that actually this error on accept and error on reject is an expectation over the cost distribution. If you don't know the cost distribution, you cannot really evaluate. So when the cost distribution, this left-hand side, is actually an unknown quantity. We do not know what is the per period cost of accept, what's the per period cost of reject, so we cannot know the minimum of the two. So the typical recipe is to add optimism. And this is done, for example, with bandits with knapsacks or bandits with constraints. There's a beautiful paper by Sipra Agrawal and Nikhil Devanur in OR 19. The main idea says that whenever you want to do learning with constraints in a complex setting, really what you want to do first is you want to understand how does your system work when the system parameters are known. So in our case, the setting where the system parameters are known is that essentially we need to know this RKA and this RKR. So we already designed an algorithm that works in this known system parameter setting. It's called BASIT. This is exactly what we saw in the previous slide. So that's the first step. First of all, you need to understand what is the skeleton of your problem when the system parameters are known. The important information that you care about is known. Now then, you're going to just estimate based on the samples that you have. You're going to estimate the sample average for these system parameters. So you're going to take an empirical mean, for example, for the error on accept, and then empirical mean on the error on reject. That's denoted by RK hat A and RK hat R. So this is the second step. So first of all, you understand how your system works with known parameters. You do not have access to the known parameters, so you need to approximate what are these known parameters with sample average. Let's take an empirical mean. And then you want to be optimistic. You want to say, instead of using this empirical mean, I will actually do an overestimate for this parameter. And I will add a bonus that will guarantee that with high probability, my known, the system parameter, the true system parameter, is going to be underestimated by this upper confidence bound, essentially. So these upper confidence bounds I denote by RK tilde A and RK tilde R. So in our case, what we will do is that we are going to replace the parameters that we don't know, RKA and RKR, with these UCB estimates, these upper confidence bounds estimates, RK tilde A and RK tilde R. And finally, here maybe we are overestimating things. So we are admitting more posts. But the nice thing about UCB is that when you are ending up admitting more posts here, you end up collecting more data, and then you're refining the bonus, because the bonus is depending inversely on the number of posts that you have for the particular type. So if maybe you overestimated the left-hand side and you admitted most posts, when you do so, you're actually getting more data. So the bonus becomes smaller and smaller, So eventually, your system is going to converge to behaving as good as if the parameters are known. So eventually, you're going to have your system working pretty well, and actually, this happens pretty soon. So this is the high-level idea behind using optimism in constraint settings. Now, with respect to the other decisions, the scheduling does not depend at all on the RKA and RKR, so we can do the same thing. But the classification actually does depend on those. So, and this could be the additional challenge. So we need to actually decide how do we deal with classification. If we do not know the RKA and the RKR, we need to estimate which of them is larger. Because in order to be able to take the minimum, this means that whenever we're not going to admit something, we are going to take the best of accept and reject decisions. So the question is, how soon do we estimate these quantities? So let's think about a simple setting with two types and one reviewer. The arrival rates will be 0.8 for the first type, 0.2 for the second type. Both of them have service rate 0.5, and the cost distribution is 1 with probability 0.6 and -1 with probability 0.4. So with probability 0.6, it's going to be bad. It will have cost 1. And with probability 0.4, it will have cost 0. And there will be some lifetimes that I will specify later. So the question, in this case, in order to do correct classification, we need to understand whether we need to find out eventually that it is more harmful to accept compared to reject, because the probability of a cost 1 is 60% and the probability of a cost -1 is 40%. Now, if the lifetimes are the same, we can see that although there are differences in arrival rates, you actually end up in a situation where soon enough you understand that the difference between RKA and RKR is positive. RKA and RKR is like error of accept and error of reject. If you know that this is positive, you know that it would be better to reject. So you can see that the triangles correspond to the type 2, the upper confidence bound and the lower confidence bound, and the circles correspond to the type 1. So you can see that soon you know that both type 1 and type 2 have higher error from accept compared to reject, and therefore the classification decision should be reject. That said, if the lifetimes are different, and you have 500 periods from type 1 and 100 periods from type 2, you can see that actually type 2 is you never really get data points for type 2. And this seems a little counterintuitive because I previously told you that the admission becomes as good as if the parameters are known. But if you know the parameters, it is never worth it to actually admit type 2. Type 2 is only going to be around for 100 periods. Type 1 is going to be around for 500 periods. It's always better to use your reviewing capacity for the post that is going to be the higher impact post. This is the type 1. This is going to stay for longer. Type 2 is a low impact post, and therefore it's not really worth it to waste capacity for something that is only going to stay for 1/5 of the time. But remember that we don't only care about enforcement, we also care about labeling, and admitting a post can help us make classification decisions. So really the highlight that I want to highlight here, the insight that I want to highlight here, is that if you apply this nice recipe that I described before, you are not really forward-looking. We tend to think about UCB as explore, exploit, but it really does not do targeted exploration in any meaningful way. What it does, it creates a best-case scenario for the current post without thinking about the future. And then it myopically exploits based on the current post. So as a result, it does not really do forward-looking exploration. And in this particular case, it is not exploring the second type because at the current round, it's not worth it to, the contribution that you will have from this particular post is not going to be worth it to use the reviewing capacity. So UCB tends to be myopic in the sense of it only considers the contribution of this post at the current round, taking an upper confidence bound because it takes the best case, but it does not think about the future effect of the label that you will get to other posts. So to deal with this, we combine optimism and max weight with some exploration that will be more targeted, some label-driven admission and forced scheduling, essentially. But I think that's an important realization about optimism-based learning that is not forward-looking, that I think could be interesting in other settings as well. So the main result is we have a square root of Lmax dependence on the regret, even when the parameters are known. And we use a congestion-aware admission rule that balances idiosyncrasy and delay and also adapts to the fluctuations in arrival patterns and review capacity that we saw that arises in practice. And we also have a dependence that a term that vanishes with t, that has essentially combines the optimistically myopic exploitation that is done by optimism-based learning with forward-looking label collection. That is important in order to learn about the low-impact types, like type 2 in our example. And for that, it's important to actually actively think about the selective sampling aspect. The fact that you are not going to get labels unless you are admitting. As I said, the square root of Lmax dependence is unavoidable even when the system parameters are known, and the typical heuristics would lead to a linear dependence on Lmax. Now, as I said before, the number of types can be pretty large. If you think about word embeddings, all the possible word embeddings can be exponentially sized compared to the dimension of the embedding dimension. So we also provide a contextual extension that removes the dependence on the number of types. Again, as I said, this is the first result for online learning in contextual queuing systems. And I want to just spend one slide to describe what are the challenges in this case. So what we did before was we said that we're going to defer if the cost of not doing so is greater than the cost of deferring. That said, as Daniel described before, when you do that, you need to keep a separate queue for each type, which will lead to overadmission. If you have a lot of different types, then you're going to keep a queue length for everything. So you're going to be admitting from every different type. And therefore, potentially, you're wasting your reviewing capacity. And similarly, we need to have a separate estimate for each type that can lead to overexploration. So the key idea to deal with the first challenge is that we're going to cluster our types into groups with similar service rates. And we're going to say, because if you think about how max weight works, really the quantity that you care in this case is the mu k, is what is the service rate in order to run it. So we're going to cluster them based on the service rate. And for the second part, we're going to express the quantities that we care about, the error on accept and reject, based on a lower feature dimension, similar to what is done in linear contextual boundaries. So our final guarantee will be something that replaces the dependence on the number of types with a dependence on the number of groups, and also has a term that depends on the difference in the service rates. Now, if you don't like having quantities like the number of groups and difference in service rates, don't worry, because we can also provide a worst case guarantee that is done by a careful group segmentation that has a dependence on Lmax to the 2/3, but does not have any dependence on number of groups, number of types, or anything of that sort. So to sum up, we started with a known cost. We initially talked about this human AI interplay, where there are three important decisions: the classification decision, the admission decision, and the scheduling decision. This is how you would operationalize most AI systems now, when you want to combine the responsiveness of AI with reliability that's coming from human reviewers, but you don't have enough capacity to actually send everything to humans. We started with a known cost distributions, and we said that actually this canonical heuristic of having these two thresholds is going to be pretty bad for various reasons. For example, it ignores idiosyncratic uncertainty, it does not take into account fluctuations, and it has a presentation bias. And therefore, we suggest the congestion-aware admission rule that takes into account what is the congestion in your system when it decides which post to admit, and it balances the idiosyncrasy and delay while adapting to fluctuations in arrival patterns and reviewing capacity. Then we talked about learning, and we saw that actually if you do optimism-only learning, which is a very nice recipe, this ignores the low-impact types and the fact that you need labels because of selective sampling. You need labels in order to classify those in the future. And as a result, we need to combine that with some forward-looking label collection. And finally, we talked about contextual queuing systems, and we saw how to remove the dependence on the number of types. And the key ideas is to have a segmentation into groups with similar service rate. I think this idea can be very powerful in other settings when you're going to think about learning in queuing, essentially, and you're going to think about contextual settings, this idea of using similar service grouping based on similar service rates and transferring information with ideas similar to linear contextual boundaries. Again, we need to extend this literature in order to hunt the queuing delayed feedback that we're getting. With that, I would like to thank all of you, and I'm very happy to get any questions. Thanks.
Thank you very much for the talk, Thodoris. Are there any questions from the audience?
I'll ask one question. Can you say a little bit more about lower bound? Because I think you said that the square root LK term was unavoidable, but
Yeah,
sorry,
so
square root L max term. But I thought maybe you knew a bit more.
yeah, no, we provide in the paper the lower bound that essentially has two types, and sorry, even with one type actually, you will need to have square root of L max because of you know, like a randomization essentially in the setting. So yeah, like the dependence on number of types. We're not providing some lower bound, but you need to pay the square root of the maximum lifetime, essentially.
And the W, does the W appear?
Good. No, the W does not appear. We don't have a lower bound for the W. If you know W, actually the W can go inside. So this allows us, we write it this way because we're going to be agnostic to the benchmark that we're going to have. So if you know W, essentially you can tune, there are two terms and you can tune them. And essentially the way to tune them, if you know W, you can put W in the tuning parameter and it can go inside the square root. Otherwise, essentially, it does not. But this way, essentially, we can be agnostic to the benchmark. The W is the strength of the benchmark. Really, the way to think of it is I'm allowing you, in order to capture non-stationarity, there is a flow of posts that are arriving, right?
Yeah.
If W is equal to 1, it says that this flow of posts that's arriving needs to be reviewed by a flow of reviewers in this particular round. The W would say that I allow you to have a window of W, that all the posts that are arriving within this window can be reviewed by all the reviewing capacity with this window. Now, this ignores delay in this system, so it's a stronger benchmark. But essentially, so it's a stronger benchmark, but it allows us essentially to capture non-stationarity. And it's motivated by this idea of capacity region in the paper by Ying, Srikant, and Yang, and then Gwen and Montiano. They are using that as a stability condition. So they are using that as I want to learn in a non-stationary learning with queuing systems. So I will impose that arrival patterns will have this property for some W, like essentially. In our case, because we are anyway over-congested, we have more arrivals than reviewers, we don't have stability in our system, right? We need to reject some post or accept some post without sending them to the queue. But we're using that in the benchmark. So that's, but the idea is inspired by them, essentially, by the stability condition that they're doing in the non-stationary learning in queuing systems. Yeah.
Thank you.
Any other questions?
So if there are no other questions, let's thank the speaker again. Thank you very much for the great talk.
Thanks.